Okay, good evening, everyone. Welcome to the final session, that is week 13 live session for the course Introduction to Semiconductor Devices, which is taught by Professor Naresh Kumar Imani from IIT Hyderabad. And I am Anant Singhal, a PhD student from IIT Jodhpur. And in the last session, we'll be discussing like most of the important topics and most of the important problems that we have done in each of the week. Uh, so like we have already ended all the contents of this course. So this was the course outline. So if I go through very quickly, we started with the semiconductors in daily life. We initially uh, went to know about what is this semiconductor materials, why do we even use semiconductors, then what are these energy levels that are discrete energy levels in an atoms. And this is how we went to know that we have certain energy bands that we need to study for the band diagram or any analysis of any material. Then we studied why do we have certain semiconductors which have small band gap or wide band gap, and why do we take a certain materials that is the most important semiconductor we know, that is silicon. Then we read about something called electrons and holes. That is, what are electrons and what are holes. Basically, holes are the vacancies that are being created by the electrons when they once go from valence band to conduction band, and at last effective mass. That is, if not in vacuum, what is the mass of a certain electron and hole if it is influenced by a certain phenomena such as scattering or certain uh, different phenomena like that. And uh, after that, in the week two, we quickly read about the carrier transport properties. What is this intrinsic carrier density? And we got to know that we have a thing called Fermi level, which basically determines whether the electron will be there in that particular till that particular energy level or not. So below the Fermi level, we have the probability of electron for an ideal case to be 1, and above the electron Fermi level, we have the probability to be 0. Then we read about the addition of impurities that we do in certain atoms, and by adding the impurities, uh, we make it extrinsic, and it basically helps in the conduction. And we read about the temperature dependence, etc., and the recombination and generation of carriers. And quickly in week three, we read, so we went from the carriers to their motion. So there can be different types of motion. We did get an overview of drift and diffusion in this particular lecture, in which how the mobility gets affected if we have an increase in temperature, decrease in temperature, etc. And then we finally had a certain current relation, which was a very basic one, which was, if you remember, it was something like NEAVD, something like that. And this was nothing but the drift component. And similarly, we also read about the diffusion part in this particular lecture. And uh, we we started making certain energy bands for a certain electric field which was generated due to this particular drift component only. And finally, we went to a certain device which was called as PN junction, electrostatics. We read about the PN junction without any bias, that is at equilibrium condition, how the band diagram looks like. And first time we get to know that we have a certain different quasi Fermi levels, that is different Fermi levels for P and N side. And there is potential that has been developed which is resulting in a barrier that we called as the built-in potential. And then we applied a certain bias on this PN junction, and so how can the band diagram look like, or what can change basically, and how the band bending change under the applied bias. And we got to know the ideal diode equation, which looked certainly like something I reverse saturation exponential of the applied bias by Vt minus 1, and this was a thermal voltage which is 0.026 at room temperature. And then we read some of the non-idealities that can happen in forward bias. We have a capacitance. In reverse bias, we have a depletion capacitance that is due to the junction created. Then some of the metal semiconductor junctions also we covered, which was Schottky and ohmic. If you remember, they were N metal and P metal, etc. And then we came to the most important topic, or the most important device for the course, or even in the existence. If I talk about in the real world application, so we started with the MOS cap structure. So MOS cap is nothing but a device having a metal oxide semiconductor sandwiched together. And we read about certain phenomena, how the accumulation occurs by applying certain negative voltage, and we go towards the positive regime. we do some depletion, and ultimately we go into the inversion. And then there is a thing called threshold voltage, after which this inversion happens, and we did a full diagram, sorry, not diagram, a full derivation of it, how it happens and what is the particular value that we need to have this to happen. Then we see some of the CV characteristics for high frequency and low frequency. So at high frequency, the minority carriers don't have enough time to react uh, to the recombination and generation, and that is why the capacitance never goes up. So this is what we read in this particular topic, and some of the non-idealities we covered, and work function difference, which was the flat band voltage minus some of the static charge that we have present in the oxide, and something like that. And some of one of the more concept was EOT. Why do we use high K dielectrics to have more and more current? And then in the later lectures, we went to this MOSFET device, which is field effect transistor, in which we have a certain additional source and drain to have the, so it does not get affected by the frequency because we have ample amount of carriers in the source and drain. And we read about certain band diagrams, etc., and what is this drain gate relationship. So this is quite important. And in the last three lectures, basically we have more of it, like more of a conceptual questions, like, okay, give me a moment. We read about more of the things to know about what is the scaling, what is this Moore's law, etc., and some of the short channel effects that are being governed by the real world devices now, some such as CLM, DBEL, etc. And we get to know some of the overviews of these. And in the last two lectures, we were more of interested in the optoelectronic devices. And this is how we ended our course outline. And so we'll now be seeing some of the most important questions that we have done in each of the weeks. And before that, let me quickly go over through, because we have only an hour's time for today. So this wave function is negative. This was one of the doubt yesterday, and we did not have any concluding remarks for that. So I hope you know that this wave function is nothing but, we know that this wave function is nothing but this is some state of quantum particle or a certain system, and it determines, basically it represents a certain state. And we have certain, this particular thing only contains all the information such as probability, we can have energy of that particle, we can have momentum of that particle, we can get to know the position of the particle just by the knowledge of having this particular wave function. So if I quickly talk about the significance in terms of the significance of this wave function or the physical significance, so it is determined by three, four things. The first was the probability amplitude, which we in general denote by the psi square x comma t, and this gives out the probability density, that is whether an electron is there or not. So this particular thing, because since it is psi square x comma t, this particular thing always falls between 0 to 1. The second thing is the normalization. So what we say that in a complete region of existence, this particular probability, if I talk about the whole region, this should be always less than, or this should be, sorry, the sum of the probability should always be equal to 0. Oh, sorry, not 0, but 1. The third thing is we can have certain operators such as momentum operator. So this is all what we have read, energy operator, using which we can calculate the energy. Now the main thing is the significance of the wave function is not directly corresponding to a measurable quantity. So what I'm trying to say, this psi reflects some different quantity. So basically this psi can be either positive or negative. It is not a criteria that psi should only be positive. This is wrong. It can be negative or positive, whatever you want. So how it can be negative or positive, as yesterday only you said that there can be a certain phase difference. So let's say I guess you might remember this, we read not finite but infinite potential well, if you remember. Can anyone tell what was the wave function that we derived for the infinite potential well? obviously time independent. Okay, if you don't remember, it was something like root 2 by L sine n pi x by L, something like that. So let's say if I take, we know that n equals to 1 is a ground state, and we say that this psi 1x is nothing but root 2 by L sine pi x by L, and it basically goes from 0 to L, whatever the L is. And if I talk now about psi equals to 2, so it goes from root 2 by L sine 2 pi x by L. So you can see for certain values of x, we are getting this psi 2 as negative. So this is only because of the interference of the different wave functions. So either we can have a constructive or a destructive interference, and either we can have a phase change. So you can see we have a 180-degree phase change that can cause, okay, sorry, phase change can cause the wave function to be negative. So there is, as such, no exact physical significance of having it negative because it is just a measurable quantity. The significance, the things that are having physically are these things, that it should be normalized. The square of that should be giving us the probability density, and that is limited to between 0 to 1. And we have a certain operators using which we can calculate or get all the information out of it. So if you remember, the momentum operator was something like this. If I can write quickly, I guess. So this was a momentum operator using which, if we know the wave function in terms of x, we get this momentum, or we get to know the momentum of the energy. The main thing is this particular thing should not blow up. By blowing up, I mean, if I, let's say if I make psi x equals to e raised to power x. Now this condition, if I say psi square x dx should be is equals to 1, this will never hold because it will basically, if I make it infinity, this is tending towards infinity. So we just need to have a measure in our mind that wave function should not be like that. It is not following any of these significant things that we need to ensure. Rest, if I take, let's say, because we in general take something, maybe something like j k x minus omega t, and if we do the exercise, we get to know what is the momentum, we get to know what is the energy operator, etc. So this is only the major concern, that the wave function should not blow up. By blowing up, I mean this should never go up against these conditions that have needs to be followed. So it is just a measurable quantity. By negative, it can means it can have a negative phase, or it can have some destructive interference due to which it can have a negative value. And if you want to see more about this, you can maybe see a quick YouTube video of coupled quantum well. So in this, what we have is we see two wells which are having finite potential, and because of one well, we have certain disturbance or interference in between the between barrier and certain something like this. It can be like this also based upon the conditions. So if you want to know more, you can see a quick video for a quantum coupled quantum well. I hope this clears the negative doubt. Wave function being negative, is it fine?
Yes, sir.
Okay, so let's quickly go through the week's content. So we started with this week one, in which we read, I have already told you what we have read. So we started with the basic concepts. So we got to know that what is photoelectric effect, sorry. Then we went to that the electron behaves like both particle and electron at the same time, sorry, wave and a particle at the same time. And this is how we started, that how is this energy is quantized, and we read certain principles that we cannot, de Broglie principle, and also the Heisenberg uncertainty principle, that we cannot have a finite value of momentum and position at the same time. And this is how, so these were some of the problems. I'm just skipping these because these are not much important, because these are quite straightforward. So this was the momentum operator that was that I was asking, that we had certain problems that it is asking for the energy. So energy operator is this, and kinetic energy is this, etc. And we get to know that how these are calculated. So this is one of the important question that can be there. You should know how should we have this wave function calculated, or if it is asking for energy, and it has given the certain wave function, you should be able to calculate all of this. Then we did some of the quick problems for infinite square well or finite square well, and this is what I just told you for the case. And this is how we calculated the energy difference that are discrete in nature. Yeah, so basically first lecture was quite basic and it only determined the basic importance of like what why these energy levels are quantized, what are the things behind it. So the main thing that you should know is the photoelectric effect. The second is this de Broglie. The third is this Heisenberg uncertainty principle, and this all leads to the formation of band diagrams, like basically the discretization of energy. So this was all for this particular lecture because this was quite basic. So let me go to week 2 quickly. Okay, yeah. So this was an important lecture considering in this particular lecture we first came to know what is this Fermi level. We read about what is this Fermi level and we did solve this Schrodinger equation that the energy is quantized. We solved a thing called density of states and how the probability comes out. And what is this semiconductor, what is this Fermi level, what is this EI. This is the first time that we got to know about this. So you should like have a good grasp on all these things, that what is this FC, what is this FE, and how this particular plot comes up FE versus energy. So as I said, for the ideal case, above or below the Fermi level we have a finite like surety that the electron is there, and after that we don't have any surety, and it changes with the amount of temperature that we are applying and all that. So we did certain questions using this, so certain basic question and then some of the assignment problems that were more or less related with these particular quantities. So you should know, or you should remember each and every formula that is written in this particular four boxes, because only this will help you in calculating, or this will help you in solving all the Fermi or the conduction band problems. So if you know these four formulas, you will be able to do any Fermi problem that has been given to you. They will either ask you the difference between the conduction to Fermi, or they can ask you between the intrinsic level to the Fermi level, etc. And you will be able to do the same. So there were more assignment problems like this only in the assignments, and some can be a wordplay. They have given intrinsic silicon, so we should know that for the intrinsic silicon, what we have is we have this n equals to p is equals to ni, so we can move forward and do the problems. And then we have certain doped silicons in which we have n type, so p is very less than n for the doped n silicon. And this is how we do all the in general very basic problems. So as I said, these four formulas, these two are for n, and similarly for p, can help you in solving any of the problem that is concerning the difference between the conduction Fermi or the Fermi intrinsic. And maybe if I, yeah, like mostly it is this only in the concept. If I see, yeah, so this is one of the gate questions. So I hope this was easier. So it was given ND1 is ND2, and you need to find the difference. So again, those formula, if you write two times for those different ND. So let's say this is for ND1, this is for ND2, and if you have a certain relation, then you will be able to get these things. So the most important thing about this lecture is just these four formulas and the concept. Yeah, that is for sure that how these Venn diagrams are coming, but the most important thing is these four formulas. If you know how these formulas are coming and what is the effect of these formulas on the band diagram, then it is fine for this particular week. Then we have week 3, which included now the motion of carrier. So again, this was a big step towards how the carrier moves now. We have just affirmed that how we are making the Fermi level, the density, the carriers, but how they move is determined by this particular week. So I'd say this was the most important week because in this week covered the drift and diffusion part. These four formulas were started as a quick revision to the previous week, and then we went towards the doping, and then we went towards the two components. One was due to the electric field and one is due to the diffusion. So due to electric field, we want to know that we have a thing called as drift velocity, which is due to the applied electric field, and we calculated all of it, and we got to know that we have a certain drift velocity which is proportional to this electric field. And we from this we derived all of that, and we get to know this is a formula that I was saying, like from the above, that the current density is nothing but nq mu n if it is an n type of semiconductor. So I wrote for that, and this is how we calculated the current density part, and we did certain numericals because of that. So this is again a quick thing: if the Fermi level is always constant for from conduction to valence band, then we have the equilibrium condition. So this is one thing to remember, that it is only in equilibrium if we have a constant Fermi level. Then we read few more relations which comes out from the diffusion calculation or the diffusion derivation that we also did yesterday kind of. Uh, so this is again some more important relation, which is the Einstein relation that gives you certain diffusion constant based upon the mobility and the thermal voltage. So most of the questions were straightforward in this lecture, like there were no as such which were very tough to go through. And yeah, so there were basic questions. So now you can see we have, let's say in this particular question, we have been given a p-type silicon bar, holes are injected such as yeah, so everything what in general they do is everything they give, and if you know the formulas directly, you will be able to calculate anything. So this is the main motive of the type of numericals that are there. But the main thing conceptually you should know is how this drift velocity has come. The second thing is how was our diffusion component has come. That is because of the concentration gradient. And if you know these two components, then you will be able to do it for N and P both. And yeah, so that is how we can have most of the questions. Also, even the gate question, it has given Na and I, so it has given a p-type semiconductor, LPL, and everything is given. And it has asked for the excess carrier concentration, so we can find it from the equilibrium and then the excess carrier concentration also. So these are all the basic stuff that was there. So again, more or less in this particular lecture, the main two formulas was maybe I can write anywhere. So one was the drift component for the J, which was I'll write the complete. So it was NQ mu n. Maybe I can write the Q outside, and mu n plus P mu P. And it, so this part is the conductivity and multiplied by electric field, and again J diffusion was sorry, dp q dp by dx. So this was q dn by dx. So if you know these things, how they have come inside your mind, you will be able to do any numericals as such in this particular week. So we have already established the motions of carrier. Now we went towards the devices. So I guess week 4 we first introduced the PN junction for the first time. Yeah, so this is week 4. So this is the first time we introduced that if we what to say, if we have two materials having a different doping, so how does it look like and how the band diagram would look like. So we read about certain junctions. The main topic was the band diagram and the band bending, how do it happens and all that. And this is how, so this was a very important lecture, I'd say, because band diagram is the basis of this course. If I give you any structure and if you can make the band diagrams visually, then you will be able to do anything or any problem. Mm. So this is how we read about how the band diagrams are made. And at equilibrium we first let the basis of this PN junction, and we have a certain built-in potential that is there, and what is the quantity known as work function, electron affinity, etc. And this is how we did the built-in potential derivation also. And yeah, and the problems were very straightforward in this. We did the derivation of electric field in the depletion region, because once we have this built-in potential or the charge density, we know that what is the charge density. And I hope so. Again, the most important part was the Poisson equation. The Poisson equation was the solver for anything. So this is charge density minus charge density by epsilon. So if we have charge density, we can calculate the electric field, because again, electric field is dV by dx. So yeah, you should know how this Poisson equation is. What is this Poisson equation? And by that we were able to solve this particular thing. Sorry. Hmm. And then at last we did some of the questions that have been given to you. So you were able to see that why this how this charge distribution or the charge density looks like for a p-n junction, and how can you calculate that. This is again important, that if we have a higher doping on the p side, let's say, then we should have a smaller depletion width on the p side, because higher doping means a lesser depletion width. This is what we have already discussed, and there were some of the problems that were regarding this. So you can see in this problem it was a higher Na. So that is what it is giving a smaller XP and a larger XN. So like that, these are some of the things that we covered. The electrical field plots, electric field plot, and then more of the things were straightforward, like calculation of built-in voltage, depletion width on the N side, P side, etc. Anything can be calculated by these a single derivation that has been derived using the Poisson equation for the ideal p-n junction diode. Yeah, so one more thing that we covered was the isotype junctions and their derivation. So it was again straightforward. Give me a moment. Yeah. So isotype junction means when we have the same doping, sorry, not same doping, same type of semiconductor, but one has a higher doping and one has a lower doping. So we did certain numericals regarding that also, and we also made the band diagrams for that. So that was again a good thing. So again, the takeaway from this was the PN junction, this which is the most important thing, because for the first time we basically band, or sorry, not band, but blended two different type of doped semiconductor together. By bending I mean, or the blending I mean, we had a single silicon bar, and at one side we did the p doping, and at the second side we did the n doping, due to which we had a certain depletion region. It is not like that practically, that we have a p, we have an n, and we join them manually. It is not the case. We have a single case, oh sorry, single bar, and we do it like this. I hope, yeah. So this is all I guess from this lecture. And then again, we straight away went to the application of bias on this PN junction in week 5, which was again straightforward. So we started with the equilibrium case revision, a certain problem which was straightforward. And then we had a certain, yeah, we started with the reverse bias because it is more or less important, because it is affecting more of the depletion width. And we saw that if we apply more and more reverse bias, we will have a wider and wider depletion width. The concept behind it, we also saw that because a negative voltage like results in pulling off more of the minority carrier towards the voltage applied, and that was causing the higher depletion width. And this is what we came to know, that in the ideal case, if we have this particular additional effect or additional voltage, we'll be able to calculate the reverse bias width that will be more as compared to uh, if we have a equilibrium condition. And we did some numericals on the band diagrams again, some theoretical part, and yeah, more or less it was just the main addition was a reverse bias voltage in this particular formula, and that is it. More of the things were based upon things. And yeah, one thing is like in general, the ideal case we consider as the abrupt p-n junction that we have. By abrupt I mean, if you have a p and n, then na is, here is na, and abruptly it is nd. So we have a instant change in the doping. So if I am, let's say this is charge density versus X plot. So here, so this is what we call as abrupt p-n junction. So most of the problems that we solve is for the abrupt p-n junction, but there are junctions which are linearly graded also, like they are not changing abruptly, but here it is Na, here it is Na, here it is changing linearly in between, and then it is Nd. So there were junctions, those for those two we have certain formulas, but in general what you will get is you will get the derivations or even the problems related to abrupt p-n junction only. And then yeah, so more or like this, and at last we solved this ideal diode equation. The derivation I guess we didn't do, but more or less we were interested in what is this reverse saturation current, and what is the effect of on the band diagram after the application of the forward bias. Yeah, and yeah, the questions were straightforward, I guess. That is all. So the main thing was here was the effect on the depletion width on application of the reverse bias, the takeaway of this particular lecture. Then I guess then we went to MOSCAP or not. Yeah, there was one lecture in between in which we did some non-idealities of the diode. Yeah. So we again did a derivation. Oh, yeah, we did the derivation for the diode equation also in the next lecture. And after that, we had the non-idealities, that is some of the metal semiconductor junction that I was talking about. So we have metal n-type semiconductor junction in which phi m is greater than phi s. So that was leading us to energy barrier. That is what we are named as the Schottky contact. And if there was no energy barrier, then we named it as the ohmic contact. That is, there is a continuous flow of electrons. Ohmic means V equals to IR. The current flow will never stop. And we did the cases for p-type metal and yeah, and this was a basic what to say basic summary of all that we have. So these all the PDFs are already there in the drive link that has been shared to you. I hope you know that all the weeks PPT are present there and all the solutions are there. And at last you already have all the YouTube videos also if you want to revise all these. And then yeah, so most of them the problems were related to the non-idealities and what is the Schottky rectifying contact and ohmic contact. So this is not like very important, but yeah, you can see if you have already grasped the previous concept, that is p-n junction on applied bias. So this is basically the same. It's just that we have certain barriers in the Schottky contact which will be getting minimized from the EC minus EF, etc. So just go through it very briefly, you will be able to do the problems. And then we went to MOSCAP, I guess. Yeah. So in this, more or less, it was this. So it is not much important, the week 6 one, but the week 7 is the most important now because we started the MOSCAP. I guess pin diode, somebody asked a doubt, so I covered a very short pin diode thing. Then we did the band diagrams for, let's say we have some random junctions to get you more familiarized with the band diagrams, etc. So if you still remember how to make this, that is very good because this was a very good thing to exercise. And then we went towards a MOS cap, starting with a constant capacitor, something like this, and how a MOS capacitor in which we have a semiconductor also in between looks like this. I hope now you be able to see the quantity or the importance of these things then that we were doing to have the final concept. Mm. So we did all the things flat band and then how the accumulation happens. So we started with a negative gate voltage. We took a case for the NMOS cap in which we have a p-type substrate to do this, and how the accumulation happens in which we remain to Cox, then how the depletion happens in which we went to this C minimum or till here, and how after that the inversion happens and we went from VT. At VT the inversion happens, which was covered in the next lecture after this, the derivation of the VT. And the problems now were again straightforward, like it is asking for different condition, what can be the case. The surface potential is the main term. Yeah, what is surface potential, and then how the band bends. So you should be practicing by making these band diagrams, let's say for a p-time MOSFET, because in general for any derivation or any explanation we in general take n MOSCAP because it is easier to explain. But if you'll be able to make the same for p MOSCAPs also, that will be good and that will be better for your conceptual analysis. Yeah, so problems were straightforward based upon the formulas that we got. Again, surface potential, the depletion width, everything is same. Then we did the voltage, sorry, the threshold voltage derivation in week 8. Week 8 is where week 8. Yeah. So in week 8, after a very quick revision of these three depletion regions, we did the calculation of the threshold voltage, which was the most important thing. And we get to know that we reach to flat band, then we deplete the carriers because of which we are getting this particular term. And we calculated the depletion region width, etc. again using the Poisson equation, which is a basis. And after the depletion, we get the inversion layer by addition of this 2 phi f potential. And we get to know that this particular gate voltage is nothing but the threshold voltage. And yeah, we covered the band diagram and then did some problems on the threshold voltage based upon the derivation that we had. So this is again very important. You should remember all the formulas for the threshold voltage. Yeah, then we do some of the high frequency, low frequency analysis, that why it is only high frequency, low frequency, and this deep depletion. That is what we covered. I guess deep depletion I covered in the next lecture, but high frequency, low frequency, I already told you the minority time difference is not enough to respond to the minority carriers cannot respond quickly. Yeah, so that is what it is. And yeah, we also did this problem. I guess someone pointed out the correct answer, that how the depletion width will change if we go from accumulation to depletion. So there will be no depletion width in the accumulation. Then the depletion width will start to increase till the inversion point. So this was increasing and this was not the answer. So I hope you remember this particular problem. If you remember, that is good. I mean, you should remember each and everything till since the course has been completed now. Then we did some analysis or some of the direct problems, and EOT was covered in the next lecture, which was a concept that is left in this particular thing. And the questions were straightforward. They can give you some diagram and you know what is COX, you know what is C minimum, you can calculate the C depletion like the problem I discussed yesterday. They were all the same, yeah. And then after this, we went towards week 9, which was a MOSFETs now. So again, a very quick overview of the previous lecture. Then we went towards, yeah, we left one inversion charge derivation in the previous lecture because inversion charge was important to cover the MOSFET. And we did this MOSFET derivations and how this IDVD and what is this enhancement. And so there were two types of depletion. So depletion MOSFET already have a channel even without the application of gate voltage, but enhancement we need to apply some certain bias. That was the difference. And we did certain derivation using which we got to know these equations. So this is for the linear region. So you should go through the derivation again if you are not aware, like if you don't remember. And again, the second one is for the saturation, which was this. So this was a summary of the NMOS and PMOS, and the one more concept was EOT that was being covered. That why do we use high K and what is the benefit of that, and how do we calculate the effective oxide thickness? Yeah, so the question was straightforward in this lecture. We have certain IDVD. They were asking for the mobility. So all of them were direct formula based. If you know these formulas, anything can be done. I think was not, yeah. So this was a very good question, which was a gate question in which they give you certain slope of IDVG. So at a certain point, you need to find a slope of IDVG at a certain different point, or not slope of IDVG, but slope of under root IDVG. So we were able to do it using the linear and the saturation region equations. So again, so this is IDVD and all, and yeah. So this was all, and this was this year's gate problem now that we were able to do very easily. So it says that the current and voltage is given for the linear region, and it asks for the GM, which is nothing but the differentiation of IDVG. And we were given everything, and the gate question was so easy, and it was, I guess, of 2 marks. So I guess you see now the magnitude of the problem. And in week 10 now, I guess it was more about the technology scaling and all. Week 10, where is week 10? Yeah, sorry. So it was more towards, first of all, a very quick overview of the previous lecture on the IDS equations, and then the body bias, it is again very important. So if we have a certain body bias, how does it affect the threshold voltage? This is what we discussed, that if we already have a certain body bias, a negative body bias, then the VTH will increase. That is, if we make VB more and more negative, then the VTH will increase. This is what we discussed, and this was the updated formula for the VTH in which we added the VSB terms. Yeah, so again, and we discussed the short channel effects in this particular lecture. So the most important were the VTH role of punch through, dipel, and channel length modulation. We also derived each and everything. So this was dipel, this was channel length modulation, because of which we have this factor. And then, yeah, we also did some of the general awareness like what are the technology that are available right now. So in iPhone 14, we got to know that it is 4 nanometer technology node, and in the 16 that will come, it is 3 nanometer technology node. And for the first time, iPhone 17 will have this 2 nanometer nanosheet technology node and all that. So these are all like general awareness. Yeah, this was a problem that we discussed again in the next lecture because we were not able to conclude it. But yeah, we also discussed this, and yeah, more or less it was this. And in week 11, if I go to, hmm, so week 11, we discussed first of all this particular problem that the VD set byte is lesser for the case for the short channel, because in the long channel we just for the short channel we have the enough critical field, electric field, to cause the saturation come earlier. And then we discuss some of the problems that were posed by some of the students. So one of the thing was parasitic BJT. I discussed what is this parasitic BJT and what is this snapback, that the effective drain voltage decreases instead of going like this. The IDVD curve goes like this. And then we came towards the main topic, which was optoelectronic devices. And yeah, some of the derivation using the Beard-Lambert's law, how the intensity plays an important role in any application, and then certain derivations. So this was again a good problem. This was some gate problem in which we calculated all of this. And yeah, and we did a very basic overview of solar cell, but we did all the numericals in the next lecture. So yeah, we came to know that we have a certain junction current from P to N, and we have a certain optical generated current from N to P, and this is how a solar cell looks like. And we did only the numerical part of the problems which are not related to the solar cell, so that were covered earlier, that were more or less related to the Beer-Sambert's law. So important takeaway from these optoelectronics are the straight away those formulas, the Beer-Lambert's law, the solar cell. So for solar cell, maybe let me open the week 12. Yeah, so for solar cell we did, yeah, these three four contents. One is the short circuit current, one is the open circuit voltage, and some of the important things were fill factor, efficiency, and one was responsivity for the photodiode. So that was all regarding the numerical problems that we did. Yeah, so most of them are like this, and we covered certain numerical problems, and this is how we ended the course. And the LED part that remains was more or less theoretical, so you can go through the lecture for that. And again, the continuity equation derivation was left in all the lectures. So in yesterday only we did this continuity equation, and we had certain assumptions for the low level injection of the minority carriers. That is we have two special cases. One is the steady state in which we don't have any electric field, and steady state means the dN by dt is always zero. That is, it is not changing with the time, and dp by dt is also zero. And there is no light, that means gn is zero. So this was the first case, I guess. The second case that we did was the concentration gradient is zero and there is no light, but it is not steady state because dN by dt is not equals to zero for this case. And we got to know that what is the excess minority carrier concentration formula. So if you know these formulas, these problems can also be solved very quickly. Yeah. So this was one thing. And then I guess, yeah, we did some of the numericals based on these two cases. And then some of the CV plots, as you asked to discuss, we covered these. And this is how we ended the yesterday's lecture. So yeah, so these were the most important parts. So let me quickly highlight. So I have already discussed these things. If I can quickly highlight for each and every week. So in this, it was the energy band formation, how the bands form. For week 2, it was the everything is important. I'm just trying to give you more important aspect. How this Fermi level has come, and even if you know the Fermi levels, then the motion of carrier, that is this drift and diffusion of carriers. So if you know that what to say, the derivations behind it, you will be able to do it. And again, the energy bands. And I would say 4 and 7 were the most important lecture because you were able to have some idea about the devices. Then again, the energy band diagram of PN junction is quite important. The causiform is important, and the built-in potential. And applied bias is again important with the ideal diode equation. And in this week 6, the most important part was this semiconductor junctions, metal semiconductor junctions. And week 7, I not make any single topic. It is everything is important for week 7. And week 8 was the most important thing was the calculation of threshold voltage and the CV measurements. Or week 9, I guess the short channel, sorry, short channel was not in the week 9. The band diagrams for the MOSFET, because we first time discussed, and the IDVD and IDVG relationships were the most important aspect. And in week 10, it was the short channel effects, all the effects that we have. And 10 and 11 are not much important, but yeah, you should be having the idea about the Beers-Lambert's law and all the things such as solar cell open circuit voltage and LED. I guess the thing that can come, I guess, is this LI characteristics and the threshold current that had certain derivation and formula. So you can go through the lecture to cover these and certain numericals that has been given, I guess, for this LED and all. So yeah, this is most of everything that I wanted to discuss in this particular lecture. And again, at last, I'd like to thank you everyone for joining. Uh, Major thank you to all those which have joined regularly, and all the best for your exam. I guess you should be having an exam soon. Yeah, apart from that, if you have any queries or discussion, we can have it right now. Otherwise, we can,
Sir,
yes,
week 1 up to week 9,
yes,
most important, sir. Week 1 to week 9,
yeah. So I have marked the most important topics.
uh, week 1 to week 9, sir.
Week 1 to week 9 only. I marked for all the weeks. I mean, is there anything specific you are asking? I'm not able to understand. Question 3
From week 1 to week 9, sir.
from week 1 you are saying, right? I'm able to hear you properly.
Yes, sir. From week to week 9,
Week 1,
uh, to week 9.
week 1 to week 9.
Week 9.
Yes,
From,
right.
most important, sir.
Yeah, the yellow ones are the most important.
Okay, sir.
Yeah. So these things you should able to know. I mean, if I would say that if you are able to know till week 4 that how this PN junction came, then you will be able to do anything in after that, because again, MOS capacitor is also certain junction only. So if you know how a PN junction band diagram has been made, so we can, or you can do anything. Like I cannot compress it more, because otherwise you will not be able to read anything. You should be at least covering these important topics if you think that you are feeling a bit weaker towards the concepts. Make sense?
Yes, sir.
Okay. Okay, so regarding this LED questions, I'll maybe you can mail me whatever the LED problems are there. I'll give you the approach. If there is some deadline, then I'll give you by today only, because it it again involves a lot of derivations and go through. So you can quickly mail me about the question 4 and 6. What are the problems that you are having? Is it fine? Yeah. So I guess this is most of it. Then, is there any particular query on the topics or anything important that you are feeling that?
Sir, how band diagram made, sir?
Okay, so okay, for that you need to. I cannot tell you quickly because I have only 5 minutes left. But for that, what you can do is you can see this particular lecture, week 4, in which I first introduced if we have different kind of material together, how this band bending happens. So for band bending, you need to first see this. So if you are able to understand this band bending, then it is nothing but electrons are going from here to here. So this will just go down because we need to align this Fermi level. So this thing will go down and there will be some band bending and you will see a diagram like this. Yeah, you need to align this Fermi. Well, you will be able to understand it just the maybe 10 to 20 minutes of the lecture. The first 10 to 20 minutes will be able to, you will be able to get how this band diagram has been made. And if you are able to make this, then you will be able to make any case. That is what we discuss in the further lectures. Is it
Yes,
fine?
sir. Fermi energy, I understand, sir.
Hmm.
I understand. But how band uh, uh, bending?
Yeah. So for
Uh,
band bending only, I have explained you the certain analogy.
sir.
So just see the first 15 minutes of this particular lecture, week 4. I have explained thoroughly that how the Fermi level aligns first of all and how the band bending is there, like in which direction they bend to. It is like analogy of this water problem. Like if we have a certain reservoir,
Okay,
so
sir.
yeah, you will be able to get it. It is very easy.
Okay,
So
sir.
yeah, just see the first 15 to 20 minutes of this particular lecture.
Okay, follow, sir.
Okay, any other thing that I'd like to maybe point out? Week 13. Hmm. Yeah, that was a pleasure. Especially you were the most regular student that attended all the lectures, so thanks to you also. So again, all the best for your exam. Then maybe we can, if you have anything, let me know quickly. We have still have 2 3 minutes. Otherwise, we'll dismiss the session. And again, all the best for your exams that you will be having. So please go through all of this very thoroughly because again, this course is very important. You will be able to get any VLSI jobs easily if you are having a concept clear in your BTech itself, and that too in, I guess, some of the students are in second year or third year. So if you have the concept clear from second year only, you will be able to do any advanced course such as analog circuits. Then we have RTL to GDS. Then we have VLSI design, etc. So if you are able to do that, any VLSI job is very easy to get. So again, yeah, this is all from my side. Like I was also doing BTech some time earlier, and I was not able to grasp all these easily. So now I'm doing a PhD in this. So yeah, this is quite wide. The scope of this is quite wide. So I hope you understand all of this. And
Hello, sir.
yeah,
Could you give us a little more details as to the scope of this subject? Like, what could be a higher end stuff of solid states?
what could be?
Some of the higher end stuffs in the solid state.
Okay, so see, in general, maybe I can stop the recording because the time has went out, and then I'll let you. Give me a moment.